Of UQCS talks. Today we have a really special presenter with us. We have the Vice President of Software Assurance at Oracle, Cristina Cifuentes, who has also done a lot of really awesome research work with Compilation, and she'll be sharing that with us today. So yeah, please welcome Cristina.
Thank you. Thank you for inviting me to give this talk. I mean, this really brings a lot of memories. 3 months ago in July, 28 years ago, I submitted my PhD thesis. Okay, I submitted my PhD thesis on the topic of decompilation. Right? And so this talk is really a little bit of a retrospective on how did I end up working in that area of decompilation, having been a student of compilation of Professor John Goff, who's here in the audience today. And this talk is dedicated to my dad, who many, many, many years ago, you know, when I was a little girl, he told me there is a future in computers, and this at the time when no one had a home computer at home. So, decompilation. This is what I used to read during my PhD thesis. And reading hexadecimal code was fine, right? And you get to know all the patterns, and you know what are the instructions and so on. And this, by the way, is the Fibonacci program from the x86 machine. Now, through the process of decompilation, you know, you end up having disassembly, so like the assembler code, right? And you can see here one particular procedure. You can see that that procedure actually is called procedure 1 for lack of a better name. It calls procedure 1 and it calls procedure 1 again, right? And through the process of techniques that were developed during my thesis, you end up creating a higher level representation of that program in what resembles C code, right? Other than not knowing the names of the variables and the procedures in this particular case, you can clearly see that in this, there's like the standard Fibonacci type of program, right? So, in July 1994, this was the definition that I had for decompilation. And to this day, I haven't thought of a better definition so far. Basically, a decompiler is a program that is going to take as input machine-readable code written in a particular machine language, and that becomes the source language, and it's going to translate it to another language, the target language, that is represented in a high-level language. Main focus at the time was C, but of course you can do this for other languages as well. So how did I end up doing that PhD work? So as it turns out, in 1990, John was running the compiler subject. This was a fourth-year subject. And those of us that were keen in understanding, how do like optimizations work and so on, we ended up taking that course. And the course also had like a component of doing a project. And you could do the project for a whole semester, so then you would get like a whole year's worth of compilers doing it that way. And then in the summer, you know, having not done enough, I ended up working with John, and Diane Corney was also there at the time. And we ended up working on this experiment on mixed compilation and interpretation, which was really, really cool. So let me tell you a little bit about this project. The success at the time, you know, was that John had this Modular 2 compiler called GPM, the Gardens Point Modular 2 compiler. And it was being used in a lot of different Unix machines, a lot of different ports of this compiler had been done. But of course, at the university, the students who at the time, you know, like PCs had become the fashion, and everyone was starting to have a PC with 2 floppy drives, 5.25-inch disks at home. They wanted to be able to run this compiler, which was designed for a Unix machine, on their PCs, right? And you can see the main differences, right? Like Unix environments at the time were using 32-bit environments. The PC was only using 60 bits at the time. Amount of memory was clearly an issue. 640 kilobytes was like the maximum amount of RAM that you used to have back then, right? The compiler would actually use 500 kilobytes before actually reading the first byte of the program.
On the note of the 640K limitation, what about like DOS extenders? Surely they existed in 1990, didn't they? Or did you actually write this not assume that there was no like DOS extenders? Like,
right, yeah, you wanted a solution that was going to be deployable to everyone rather than requiring students to jump through hoops, right? So in any case, the compiler would generate object code for various different machines just using a translation from the abstract syntax tree representation through a C code generator and then generating the code through the C compiler or through assembly, okay, and generating the code that way. So the idea here was that we could actually add like a third type of translator, and that third translator could actually work on an intermediate representation that was called decode. And this intermediate representation would actually allow us to then focus on how to generate like the object code directly for the x86 for the PCs, so that this object code could be linked by the Microsoft linker at the time. And doing this, and using like the Turbo C compiler at the time, you would be able to do all of the initialization in 400K, which already allowed us to have more memory to actually run our programs, right? Or the students' programs. So then during the compilers project and the summer work, during the summer, like there were 3 of us actually working on this, then we got it to work complete end to end, right? You have like, my part was really writing like the interpreter for this decode machine, right? And being able to generate x86 assembly code. And this was 8086 at the time, what we were generating, okay? And hence you can see that through this project, I got very used to like reading assembly code, being able to debug assembly code and so on, right? And hence the leap, like later that time was pretty simple, right? But for the students, this was like a great success because now they were able to take the compiler and be able to run their programs at home without having to be here at uni because, of course, things were very different back then compared to what you guys get these days. So in 1991, I actually started like my PhD work. And the focus was reverse compilation techniques. And where did that idea come from? Well, John and also Professor Bill Kiley had teamed up together, and they had been discussing a lot about these ideas on, is it possible to have a reverse C compiler? Okay? And one of the things that was happening at the time was that with PCs, there was a proliferation of viruses that started happening around the place, right? So viruses were new, they're all in binary form. Can we actually be able to decompile, reverse the compilation process to be able to see a little bit more into them? And so this was a proposal that was submitted to the Australian Research Council. It was funded, and through that proposal, I was like one of the PhD students. But then I also ended up meeting Mike Van Emmerik, who's also here in the audience with us today, who worked in this project as well for some of the more like engineering side of things. And it was really interesting working with Mike because clearly we came from very different perspectives. He wanted to build something. I wanted to understand how we're going to create algorithms to generate what he wants to build. So we divided like different aspects of the project, right? Now, throughout the PhD work, there were a lot of new techniques that needed to be developed. One of them was like the whole decompiler architecture. What would we focus on? Like how would you go? Like what are the steps to follow? There was also like how to recover control flow, because clearly if you can see if statements, loops, and so on, much better than just seeing go-to statements around the code. Also needed to have data flow recovery because you end up with expressions that are very long just because there's all of these registers that the x86 machine is using, and in reality you want to disappear a lot of those registers to be able to have expressions that really resemble more like what you normally see in a high-level programming language. And you know, after 3 years, it was kind of like, oh, I started looking into type recovery, but you know, I had done enough, so we went like, okay, I submit here, right? So the result of that was the DCC decompiler, which was written for x86 and the DOS operating system. Notice that Windows became only popular around that time, okay? And it was doing the compilation to the C language. Now, in terms of the architecture, you can see here that with the architecture, the idea was to take the binary program at the top, be able to do some loading of that program, how like the machine would actually load it up, right? And then you could start doing your parser like any compiler, right? Like the compiler is going to parse your program, right? Like all of your statements and so on. Well, here we're just going to parse all of these machine code to be able to understand what instructions, machine code instructions, it actually maps to. And clearly you can see that if you go down this path from the parser to assembly code generation, you have a disassembler, right? But clearly to be able to have a decompiler, you need to lift the level of representation. And so you need to abstract a lot more, right? And so there was semantic analysis, trying to understand what's the meaning of the instructions, then your data flow, control flow, generate the high-level language program. So I'll give you like a few little examples, but key to the whole concept was this idea that there needs to be a high-level intermediate representation in there, so that we're starting from the assembly instructions. Those assembly instructions need to be lifted up to a high-level intermediate representation. And you can see that my language was very simple, right? I only had like 5 different types of statements. You can have an assignment, you can have a jump that is an unconditional jump, or you could have a conditional jump, right? You can have a call, and you can have a return. And with that, after you've done like control flow, data flow recovery, you can get like a lot of the structure from your programs, right? Notice that I also had this concept of pseudo high-level transient instructions, like push and pop. And that was because as you're going through the process, you're trying to remove all of these instructions, but initially you still need them while you're doing some of the analysis, the transformations. And when you look into data flow analysis, hey, it was a lot of the techniques that you grab from your favorite Red Dragon book, right? Here's like the whole list of the various different type of optimizations that I was using, but I was not using them for optimization the way that the compiler uses them. I was using them to remove stuff from all of the assembly code, right? And so there was dead register elimination, dead condition code elimination, a lot of very standard type of techniques. And I also looked into some of the data flow papers from Frank Allen and John Koch from the 1970s to develop some of these techniques. So here's a very simple example. Like you can take like this piece of assembly code, right? And then you can convert it into one single assignment instruction. And so you can read it the following way, right? There's a move AXDI. So in my intermediate language, that becomes an assignment. AX is going to be assigned DI, right? And notice that I keep like definition use chains. So definition of AX happens at this particular statement, like statement 28. where is it being used? It says that it's only being used in statement 30. And when you look at 30, well, 30 is actually implicitly using the AX register here, right? If you look at the statement 29, assigned to BX 10, well, in this particular case, BX is being used in two different statements. So by tracking like definition use chains, right, you're able to then start collapsing information, and you can see that once you start doing that collapse, right, like anywhere that you have like AX, it's only being used here in this statement 30. Well, this AX gets replaced with DI, right? And you keep on doing that with BX and everything, and at the end of the day, then you just end up with this high-level instruction. Assign to register SI, DI, present hexadecimal A, right? So that gives you an idea of how you're actually using like the optimizations. You're really just using them to compress, remove out all of the statements, like the registers that you have in there. Now, where do condition codes come into play? Condition codes are always going to be used by a lot of the conditional statements, right? So whenever you have, for example, a compare instruction, the compare instruction itself is going to define several different types of condition codes. The sign flag, the zero flag, the carry flag. And then when you have a conditional jump, like in this case it is jump on greater than, it is using some of those condition codes. So in this case it's using the sign flag and the zero flag. You do use definition chains here as well. And then you know that these two statements, right, you can collapse them together into a conditional jump AX greater than BX. Right? And notice that there could be statements in between, right? Like you could have 5, 10 different statements, and if those statements are not actually modifying the condition codes, you can still collapse these instructions in exactly the same way, because that's what the use definition chain is tracking for you here. And similar for the earlier example, you could have statements in between, of course, right? So that's kind of like the data flow works. So now when you start looking into the control flow, what do you want to do? Well, here, like there was a lot of different works that talked about, because at some point in time, early in programming, there used to be a lot of go-to statements, and everyone was like, how we delete go-to statements, right? Like, so how do you actually structure the programs, right? And so you can see that there's a lot of like very common type of representative type of control structures that you can find in any programming language, right? Like you can have a statement on its own, a statement followed by another statement, or you can have a conditional branch, kind of like an if, then, and is that when you have like random go-tos throughout the program, you may end up in a situation where you have an irreducible graph. And the canonical irreducible graph is this one here at the bottom. And you cannot reduce that graph any further. So whenever you have an irreducible graph, you know that part you will need to use a go-to to be able to break out of it, right? Even if you keep on collapsing, if at the end of the day that's an irreducible graph, well, you have to stop there. You will need to use a go-to, and hence go-to is one of the instructions that was also used in this representation, right? Now, you also have like these other type of thinking about what happens when you have short secret evaluated expressions. A short secret evaluated expression, like you may have if condition A or condition B happens to the following, right? The way that the compiler represents that is by actually breaking it down in a graph that looks more like this one, the one on the left-hand side, right? It's going to do part of the test first, and it's going to do the second test, and then it decides, okay, do this, otherwise we go out, right? So if you do this analysis in this case, well, you're actually trying to convert this type of graph into this representation that will represent for you the fact that you were using an OR in this particular example. Similar thing can happen with an AND so on. Okay? So clearly, this representation much easier to understand compared to this representation right here. Okay? And then, you know, like while I was doing all of this, Mike was looking into this other side of the problem where it was like, hey, compilers make use of all of these libraries, and we're not going to be decompiling all of the code for each of the libraries to then try and understand what they are, right? So there was this whole idea about generating signatures for the libraries and being able to keep track of those signatures so that then when we add the signatures to the decompiler, we're able to determine, okay, this was like a printf statement call, and therefore we can replace that call by the name of the actual library function instead of like trying to decompile all of the code for printf, which would be pretty long and messy, right? And similar also like with compiler signatures as well, right? That there were common type of compilers being used. Each compiler does certain things before they actually invoke the main of the program. So there were signatures that were generated for those ones so that we could also focus on here's the code from the main onwards, right? And here's all of the other code that the compiler needs to set up in order to set up the program before it runs. So all of this work, you know, at the time, you know, being a PhD student, something that is very important is to publish papers. And so you do the right thing and you submit papers to the Australian Computer Science Conference, and your papers get rejected every year, one after the other, right? I was like, oh, okay, this is very interesting. Why is that? So then I sent a couple of papers to the Latin American Computer Science Conference, and they were accepted there. I was like, well, this is kind of weird because it's exactly the same material, right? And then I went, oh, let's submit it then to PLDI, like one of the top conferences in the programming languages space, right, like in the US, and it was rejected, right? And then that year, it was funny enough, like John and I were there at the conference, and there were all these professors asking me about the techniques and how it worked and so on, and I'm like, oh, I know who were all the referees here. Yeah, but nevertheless, you learn something from all of these rejections from the papers, right? And then you go, okay, I need to complete PhD, time to focus on journal submissions. And so the PLDI paper is the paper that I submitted to the journal on software practice and experience. And this paper is the paper that has been cited the most out of all of the papers that I've written. And it was funny, you know, like a lot of like people have read it, but one of my friends was doing his PhD in France. And one day he sends me mail and he says, hey, Cristina, I was sitting here next to someone in the bus who was reading a paper from software practice and experience. And the paper looked interesting, so I started reading like what he was reading. And then at the end, when, you know, like they arrived to the university, I asked like, oh, what's the name of the paper? It was your paper. So that was like super cool, like to hear like from him. First, I hadn't heard from him in a long time, but then, you know, actually know that people were reading these papers, you know, it was like, oh, wow, people actually read the papers, right? And then there were other papers that I did end up publishing as well. And hence, PhD was awarded, and here's like John and I with our floppy hats at the time. Now, the years after the PhD, I joined the University of Tasmania as an academic, right? And while I was there, you know, like now we have progressed through 3.5-inch floppy disks. And one of the things that started happening was that because Windows had become popular and everything, you know, had been written for those, okay, we need to upgrade to Windows, you know, you start doing this type of thing, upgrade to what is the new version of the OS, and so on, answer questions, you know. And I started getting like all of these questions coming through email from various different places. And you have to remember that at the time also, the internet was kind of new, right? And you couldn't just start shipping like super large type of files everywhere because there were quotas, there were restrictions, and so on. And we used to get also like postcards at the time, like asking you for, can you send me a preprint copy of your paper, right? So one of the things, you know, like with all of these questions, you know, was that the questions tended to be very similar in nature, you know. Can I get a copy of your DCC decompiler? And I'm like, well, I cannot ship it on email, right? Can you port the decompiler to a different architecture, you know, whatever the architecture like different people were interested in? And I was like, well, you can do it, it's very simple, but then they need access to the code. And so at the end, you know, what I ended up doing was writing HTML code just to be able to make it available, right, on a web page at the University of Tasmania. And one day, the IT guy, the computer science, comes to my office, and he says, Cristina, what do you have on that page? You know, you have a web page. What do you have on that page? And I was like, well, I just have like my PhD thesis in there, right? Like I had the thesis, I had like the code for the DCC decompiler. I had open sourced it, you know, at the time when not many people knew what open source was all about. I had used like the GPL license also on purpose, right? Because I had some localies at the University of Tasmania. So there were all these things, and you had to write HTML code by hand at the time. So those were the type of computers that we were using at the time. And it was superb, you know, like many people were downloading and so on. Then, you know, I came back to sunny Queensland, to the University of Queensland. And even though I started like working on other areas, right, there was work that we continued doing in the area of decompilation. It was more about like bringing information into like a whole main page, the decompilation page. And I was working with Bill Claudel, who I actually met in Minnesota at the time in 1996. And he had worked in very, very earlier type of decompilers with Morris Olsted. And when I visited Minnesota, I mean, he was showing some of these like really early memos that they had from the Univac machine and how they had all of these ideas on doing the inverse of compilation and what would be some of the steps that they would implement and so on. This one at the time was a proposal. They did have various different implementations for different types of decompilers at the time. And then while being here at UQ, there was also like this consultancy that Mike and I worked on, where we had a customer that came to UQ and said like, oh, we want this team to look into this binary because this binary stopped working and they know decompilation. And after looking into the binary, what had happened? The binary stopped working after 30 days that a certain employee had left the company, and there was a time bomb in the actual binary, right? And you could see you didn't need decompilation per se. You only needed to understand assembly code to be able to understand that bit, right? So that was kind of an interesting consultancy that we did here. Now, at the time, you know, like my team here at UQ, we started working on binary translation. And with binary translation, you know, I kind of see it as the cousin of decompilation because you are kind of like lifting the level of binary code into an intermediate representation, but then you then need to bring it down to binary code, executable code again, right? Now, one of the things that we realized because of all of these questions, like, can you do this for another machine? And by then, like, Pentium existed, right? There was also like the Alpha machine, there was Spark, there was MIPS, and so on. Well, how about we start encoding a lot of this information in such a way that we can just reuse it, like the implementation, there'll be specifications on the side, and then the main implementation, we just grab those specifications and be able to generate various different pieces of code for you. So we teamed up with Norman Ramsey and Mary Fernandez. Norman was working at the University of Virginia at the time, and he was interested in encoding all of the assembly instructions for the purposes of compilation. And we were interested for the purpose of the inverse, for the decompilation. So we teamed up those resources to be able to work with this. We also looked into various different binary file formats, right, like to be able to specify all of that information, and this was work with a PhD student, David Ang. We also looked into the semantics of the machine code instructions, right? Because if we had the representation, you can think that's the syntax. Well, what is the semantics? We need to know what these instructions do. And this was work with Shane Sendall. He was an honors student at the time here at UQ. Initially, we used object set specification, but clearly this was not as simple to use compared to a representation that is a little bit more textual that you can actually parse more easily. And so we ended up with this type of representation to represent the semantics of the machine instructions. With Doug Simon, also an honors student here at UQ, we ended up creating the configurations for the procedures, right? Like because different instruction sets are going to, and different representations are going to use like different types of products, epilogues when you invoke a different procedure or function and so on. You also need to understand where parameters are being passed, and are they being passed on the stack, are they being passed on registers, and so on. So this is the type of information that was being encoded here, like through epilogues and products and so on, right? And then Java was becoming a thing, right, at the time, and Java had bytecodes. And then with Trent Waddington, who's also here, Trent was one of the new students at the time, and we went, how about translating to bytecodes, right? Because it's an easier representation also to be able to manipulate, but it was different to the other ones because we were taking like the front end into the high level representation, and then we needed to lower it down to a stack-based representation for bytecodes, right? So that was also like a pretty interesting type of work. Now, while I was here at UQ, there was this message that one day came on email from the US. And it so happens that there was a company called Source Again that had been founded in 1998. And the company had basically implemented a decompiler for the Java language. Right? So you would take like Java binaries and decompile into Java. And you know, I remember like my colleague John Harrison, like next door neighbor here in the same building, right? And he came, can I see that email again? You mean like a whole company has been created around this work that you've done? And we're like, yeah. He's like, wow, okay. And here at UQ at the time, there was also like discussion about like various different type of startup companies and so on, but this was very, very new. Not many people were into startups, and the conditions were very different to how they are today. Now, there was also this discussion, you know, like around like the year 2000, right? That everyone was concerned like, oh, how are we going to upgrade all of these programs that are in binary representation, source code is missing, and so on. This American company, the source recovery company, was actually looking into like the compilation techniques, but mainly focusing on COBOL type of languages, assembler, MBS, and so on. Yeah. But at the time, there were discussions as to whether they could buy DCC. And we're like, what do you mean you want to buy DCC? DCC is open source under GPL, right? You see what I mean? But there was all of these type of things happening, and you know, like back then you needed to have friends to really understand what was going on. It was very lucky, you know, that I met Anne Fitzgerald, legal academic at the University of Tasmania, because we had endless discussions in this space. Now, we were so keen at the time that we created this workshop on decompilation techniques. And this was in Stuttgart in Germany in 2001. And so here you can see Mike, same jumper, hey. And there was Trent, different. Yeah. And of course the shortest one is me, but then you can also see who's here. Ilfak from IDA Pro, IDA Pro. Right? So anyone that is into this assembly would know that IDA Pro was created by Ilfak, and this workshop was superb because all we could talk about were all of the various different ideas and techniques that we were all creating. And you know, Ilfak was already having all of these ideas of creating a decompiler, which these days, you know, like is available, right, like through his company. And we were coming in with like, hey, we have also these ideas as to how you can have a debugger that can encapsulate a decompiler straight into it, so that rather than disassembling, you know, when you're debugging, rather than disassembling, getting all the assembly code, you could be getting like other type of information and so on. So pretty cool. And then there was like, you know, like some more work being done. This Ian Stroger was a student of John's. I ended up co-supervising, you know, C++. Oh, it has virtual tables. Now we need to start looking into other types of things. We ended up finding 3 different types of patterns that would encapsulate a lot of that. And then both Mike and Trent ended up branching out into their own decompiler, the Boomerang decompiler. And they used it as a playground for various different types of ideas that they had. They started looking into Spark binaries as well, Pentium binaries, looking into like the single static assignment form representation as a more compact representation, like to see how well this would work. And in the end, like Mike ended up getting his PhD in the decompilation area through use of this SSH representation as a way of doing the decompilation in a simplified like data flow type of way. There were also analysis of indirect jump calls, which was something that wasn't done much in my thesis. But clearly you can see that, you know, it's kind of like taking it to the next level. Like, what are some of those other areas that haven't been looked into? And so this was also really great work. And that was a PhD like here from UQ. Now, while, I went to the US, and while I was in the US, I ended up doing this consultancy for a company that I cannot tell you which company it is, but one of the things that they were interested in was that there was all of this code that was being written on-chip processors. And they wanted like to be able to understand how to write a decompiler for these on-chip processors for the code, like to be able to understand it. So, you know, like a lot of the work, it was really good, like to be able to test IDA Pro at the time, because it was like, hey, I've never used IDA Pro in someone else's like chip out there. They send me the chip, let's see how it works. Things worked out really well, and from there we were able to explain how it like the whole decompilation process worked out of there. And then in 2005, you know, I met Chris Weisapol. And Chris Weisapol, at the time was with Symantec, right? And this was when Veracode was being created. You can see that he used to be like the director of development in Symantec at the time. And they had been working on this tool that would take binary programs and they would look into vulnerabilities in that program, right? And then it would report to you, oh, in this code you have, for example, a buffer overflow, or you have a SQL injection, whatever it may be, right? Like different type of vulnerabilities, right? So kind of like static code analysis that it's widely used these days. But they were doing it at the binary level, and they had kind of like their first initial prototypes, and so they were using like the techniques, of course, that came from my PhD work. And so there's an example of another company, right, that was being created. And the venture capital investor actually came and asked, like, hey, what is your opinion on this, and that, right? And based on that, like they end up getting like the funding. Veracode was actually created as a startup company, broke out from Symantec, and these days you all know that Veracode stood around working on a lot of various different type of tools around the place. And these guys actually worked on, exactly, YouTube ended up working for Veracode, yeah, and then Trent is still working for Veracode these days, remotely. So, like throughout the years, it has been very interesting meeting a lot of people. You go to a conference and there's always someone that knows about like the work. They want to tell you a story or how they've used like decompilation for something, or what ideas they have. Very, very interesting. Things that are a little bit funny sometimes, like sometimes you end up with that one-way communication. Like they just want to know more and more and more from you. What do you think about this? Why do you think about that? But they don't want to tell you what they're working on. And those ones you go like, oh, okay, yeah, interesting. Of course, like there's been like many different compilation papers that I end up reviewing throughout different conferences and journals, right? And perhaps like the coolest introduction was in Singapore, like Rich Johnson. He was at Hack the Box, and he goes, hey, come after, like I finished my training. And I go there because I was in a different event at the time. Go there and then, let's go and meet these guys. Hey, you guys remember that paper on decompilation techniques, blah, blah, blah? And they're like, yeah, here's Cristina. And I was, oh, can I shake your hand kind of thing. Yeah, it was really fun. So in any case, 2019, the NSA released its own decompiler, Gitra, right? And then, they open source their decompiler, and everyone's like, whoa, like decompilation now is like really popular kind of thing, endorsed or something, right? Now, clearly they had been using the decompiler for various different types of things, including like looking, analyzing malicious code and malware, right? And if I kind of think back to like the ARC proposal from like John and Bill many, many moons ago, viruses, right? With these days, malware. And clearly, it's a little bit of the same trend, happening all around the place. And hey, Gitra provides debugger support. And we go like, what was that paper that we presented at that workshop also many years ago, right? So many cool ideas, great implementation. And so what have we done? Like with Gitra, just very briefly, like a project that myself and Mahin Chandramohan, a colleague from Oracle Labs here in Australia, and also student Haok Tan, one of the UQ students from a couple of years ago in 2020, right? we worked on ColdPress. And, you know, like my moment was like, more like mentoring. So I should say how she did all the work. And Mahina and I were coming with all of the ideas as to how certain things could be done and so on, right? But the idea here is like, how can we fully automatically extract indicators of compromise from Windows binaries, right? You want to be able to use various different type of techniques. Now the implementation itself was making use of the Gitra decompiler. Like here's a disassembly from the WannaCry malware. And the idea with ColdPress was that you can take like all of those samples here on the top left-hand side, right? And then you're going to have various different type of tools that are going to run over the code, and you can have various different types of profiles and so on. But here, you can have Gitra, you can have Radar2, which is another type of decompiler. You can have Beanwolf to be able to unpack various different type of Windows binaries that are all fully packed these days, right? And you can get out of that like a lot of information, and this information you can then start like teaming up with threat intelligence type of tools to be able to really get more information out of it. The result of this project is open source in under the UQCS GitHub area, okay, and it's called ColdPress. So here's some examples of what the decompilation would look like to extract indicators of compromise, right? Here's a sample report for like WannaCry, right? Written in JSON, but you can see like you have information that Beanwolf produced for you, information for Kappa, information for exports and so on. There's different functions, graphs and so on, and you can expand all of this information, right? There was also like, here's information for the various different Kappa rules and information about interesting URLs in case they're of use, right? Interesting strings that were found in the binaries and so on, right? So these, you know, like being indicators of compromise is just there like to help you with your whole threat intelligence type of environment. So, and the fact that you could automate these is like significant point, right? Like because a lot of like analysts, they tend to work like very manually, and clearly like these days you really need to scale up and be able to do this in a much more automated way. Clearly, doing everything statically is not going to give you all the information. Like for malware, you still need dynamic type of techniques, of course, but you know, combination of static and dynamic will give you the best of both worlds at the end of the day. So if we now go back and look at what are areas in the decompilation of binary programs that are still unresolved, areas that you could look into in the future. Well, there's still like this whole area of alias analysis, right? Like if you have two pointers, are they pointing to the same thing? Are they pointing to different things, right? Like that's alias analysis. That is something that hasn't been analyzed a lot in the context of decompilation. You can have analysis that are interprocedural, context-sensitive, path-sensitive, and so on. So you can bring all of that program analysis into this space, right? And clearly, type recovery of high-level, like types, really important as well. Something that is also missing to a certain amount of. Now, very many different types of projects that have related to compilation, you know, like throughout my career. And these days, you know, I'm focusing on software assurance as well as application security tools. And we're building, you know, like a very large organization in this area. And of course, we're also hiring in this space. So, to conclude, when Bill Claudel and I were putting together like this decompilation page, at some point in time, we went, hey, who's the father of decompilation? And we went, that title goes to Maurice Halstead. because of all of the work that he had done in the very early days, and it expanded from 1960 to 1978, right? Various different types of decompilation projects. You can see like our notes as trying to correct like the pages that we were creating at the time, right? And now these days, I've been very fortunate to have earned the title of Mother of Decompilation. Thank you.
Does anyone have any questions for Cristina while she's still up here?
Yeah. You mentioned like a couple of slides back, you mentioned like the trouble of like getting like procedure calls or like decompiling procedure calls or something like that. Was that something like that? The problem with that? There's a couple of slides back, I think so.
You mean here?
No, like when you're describing like the original one, like back in the day.
Ooh, I wouldn't know like where.
Oh, it'd be like as you like describe your original like
Yeah, one of the first ones.
The user
Yeah.
libraries,
Yeah, the libraries.
Oh, the libraries. Okay.
Yeah, that's what I meant. Like decompiling library names. Like these days, like modern like binary formats will usually like store like a symbol table with all like the names of all like library symbols in there and signatures and like that. But I guess was that like still the case? Was that also the case with binary formats back then, or was that not the case? Did it not have like a general symbol table where?
Trying to answer the binary that Cristina was often decompiling was statically linked,
Oh, okay.
right? And generally the library had nothing in it, not even the name of the function.
Yeah, because when you do like an NM like a binary file,
Right.
it will give you like the symbol table of like all the function, and you can say like all the functions that this program uses. So that wasn't the case. Right?
At Veracode, my name's at Veracode, that we are purely cooperation. We are not antagonistic to others.
Yeah.
So we ask customers to give us full debugging permission.
Yeah.
And customers sometimes comply, but sometimes they don't. They go to trouble. But we say, if you don't give us line numbers, we can't say you've got a security.
Yeah.
That generally gets them to comply.
Okay. Okay, yeah. So it might have been back then, because I know about like original like the DOS executable formats were like primitive, but I didn't know they were that primitive, like not even having like a symbol table inside.
Yeah.
This has to be like really small to fit like, was it like 60, not even 640K, 64K segments, wasn't it, or something like that?
64K at some point in time. So yeah, that's where we all started.
well, 16 bit addresses